Right, hello again, everyone. My name's Doug Mason. I'm a Principal Engineering Geologist with WSP in Wellington, in New Zealand. So welcome to this webinar series. This is the first of three. This is a global series. We're going to present some of our recent work and other work into resilience to geohazards and some of our lessons and findings from this part of the world. So we have 45 minutes today. So my colleague Brab is going to be presenting this first webinar, 30 minutes of presentation and then time for Q&A at the end. So just a couple more housekeeping items. The presentation slides from today will be available to download in the handout box on the GoToWebinar control panel. And as I said, there will be time for Q&A at the end. So please ask questions in the question box as well. Right, and without further ado, I'll hand over to Braba.
Thanks very much, Doug. So today we're going to talk about resilience, climate change, sustainability, and how we can move forward to deal with that. So welcome, kia ora, good day. A little bit about myself. So my name is Prabhaharan, and I'm a National Technical Leader and Technical Director in Wellington, New Zealand, and I specialize in geotechnical earthquake engineering and resilience. A little bit about me. People often ask me what my first name is, but I just use one name. So because in Tamil, I'm a Tamil and we use only one name. So I came to New Zealand about 35 years ago from the UK, and previously having worked in the United Kingdom, Malaysia, Singapore, and Sri Lanka. I started off focusing my career here on geotechnical engineering, but then I found that it was important to broaden my outlook to help organizations understand resilience of their infrastructure assets and help improve the resilience of communities. So my passion is to enhance the resilience and sustainability of our society. With that in mind and realizing that important, I formed a risk and resilience team about 15 years ago here. And now we have about 150 geotechnical, geology, and seismology staff in our team. And that's among 2,500 across 35 offices in New Zealand. So today we're going to talk about natural hazard impacts. We'll look at some hazards to get our mind in that frame. And then we'll reflect on some climate change effects. And then look at how resilience and sustainability are looked at and defined. And then the main part would be to focus on some case studies, through 4 case studies to illustrate this. And then we'll look at some of the key concepts developed through this work and conclude. And as Doug mentioned, we'll finish with a Q&A, which will be facilitated by Sharon from our Canadian office. So natural hazard impacts. So just this year, in February, we had a large cyclone, Gabriel, which hit the northeast part of New Zealand, and you can see there on the left-hand side. And it caused a lot of damage to our infrastructure and suffering for our communities. And just a week earlier, in late January, on Auckland Anniversary Day, a big storm hit Auckland, which is our biggest city in New Zealand. And again, that caused a lot of damage to properties, grief for people, and affected our infrastructure. And we are still recovering from these events. And a couple of years ago, we had the Marlborough storm. Actually, we had that in 2 consecutive years, which again impacted a lot of properties through landslides and mud flows, as well as affected a lot of infrastructure through river erosion and landslides. And just in 2018, we had Cyclone Gita, which again impacted the Kaikoura area, which you can see is in the northeastern part of the South Island, again with a lot of damage to properties. And 2016, we had a major earthquake, the Kaikoura earthquake, which was magnitude 7.8 on the Richter scale. And that again hit the Kaikoura area, which is located in the northeastern part of the South Island. And it closed the National State Highway 1 and the railway line for 9 months to 15 months. Same year, I had the opportunity to go to Japan to learn from the Kumamoto earthquake. And again, you can see the amount of destruction caused by that earthquake, which was about magnitude 7. And the biggest damage and destruction came from the 2010-2011 Canterbury earthquake sequence. And that hit Christchurch on the east coast of the South Island, and which is the main city in the South Island. And one of the defining things of that earthquake was the amount of liquefaction, lateral spreading, and damaged. As you can see in this picture, some new suburbs were completely damaged by this liquefaction events. And you can see the infrastructure was also damaged. So, and then a few years before that, I had the opportunity to look at the Wenchuan earthquake and learn from that event in 2018. And I just want to show this city of Beichuan, which was a nice, beautiful city in the mountains. It was damaged by the earthquake, hit by landslides during the earthquake. Then subsequent storm events caused mud flows and landslides and flooding, which completely destroyed the city. And the city had to be shut down and abandoned. So you can see the impact of natural hazards on our built environment. Let's now reflect a little bit on climate change. So this is a piece of research done in Europe, looking at the changes in rainfall intensity between 1950 and 2013. In a lot of times with climate change, people talk about the increases in temperature and rainfall, and often they talk about the averages. But what that research found is that, yes, there is an increase in the averages, but more importantly, there was a much higher increase in rainfall in the extreme events, say like the 1% severe events or even smaller than that. So this increase in severity of events is very significant. And on the right-hand side, you can see this graph indicating that not only is the severity increasing, but the frequency of these severe events is increasing. So that's a key thing we need to keep in mind in our work. So often climate change, people reflect on sea level rise. The sea level rise happens gradually, but we are already seeing this increased severe rainfall events, storm events leading to landslides, flooding, and river flows, which we as engineering professionals have a key role to play to manage them. So these climate change impacts lead to disrupted communities, large economic losses, the impact on the resilience of our infrastructure, and a large carbon footprint for repeated reconstruction and recovery. So let's look a little bit about resilience and sustainability and what we mean by that. So living in an era of uncertainty, we need to engineer through extreme earthquake events. Here in New Zealand, we had the new National Seismic Hazard Model published just late last year, which significantly raised the risk from earthquakes. Our knowledge of that risk is now much higher. We also had extreme weather events, as we saw at the beginning, and we need to decarbonize what we do in our sector to reduce emissions and arrest future changes in climate. So in this engineering, we also need to deal with increasingly people want to develop hazard-prone land. So how do we manage that through appropriate measures. And while doing all this, we also need to be cognizant of the inflationary era we have, where the work, engineering work, the cost of that is escalating quite significantly. So in order to improve resilience to natural hazards, we need the ability to continue to provide functionality despite these hazard events. And our infrastructure and our built environment needs to be able to absorb these shock events, adapt and recover quickly to provide functionality. And we need to adapt also to progressive events like sea level rise to provide functionality. So you can see that emphasis on two important things. One is functionality and the other one is recovery. So resilience is the ability to provide ongoing service and quick return to functionality in the face of these adverse events from an engineering perspective. So I often use this simple graphic. We have a normal level of service or functionality, and then suddenly we have one of these events which leads to a complete loss or partial loss of this functionality. And then it takes some time to recover. So this green triangle is an indicator of our resilience. So the smaller that green triangle, the greater the resilience. So from a sustainability perspective, people often define sustainability as being able to meet the needs of the present generation without compromising the ability of future generations to meet their own needs. So we can reframe that from a climate change and resilience perspective to say meeting the functional needs of society without compromising the environment now and into the future. And you can see the economic, the society and environment are all interrelated. So eventually society is at the heart of everything we do. So communities need to be able to sustain and thrive in the face of these hazards so that we can have resilient communities. To have resilient communities, we need to ensure the functionality of the built environment, because everything we do in engineering, whether it's a house or an office block or infrastructure like roads or water, everything is to provide a functionality for our communities. To ensure that, we need to make sure that we take into account the resilience of our built environment. And when we design, we need to design keeping in mind resilience is critical to our built environment. Our current design approaches were developed in places and in stable environments in the years gone by. We are now, particularly in New Zealand, living in shaky isles, so we don't have a stable environment, but also we have climate change and all the uncertainty which we need to deal with. So let's look at how we can deal with this through some case studies. So I'm going to talk through 4 case studies, starting from simple ones to more impactful ones. So the first case study is shared path, a cycle and walking path between Naranga and Petone along the Wellington harbour front. And one of the key objectives there is to reduce the reliance on vehicles, cars, and therefore reduce greenhouse emissions. So one of the key objectives for this is the resilience to natural hazards and being able to cope with future sea level rise being next to the sea. So I was engaged at WSP to provide advice on design to enhance resilience and prepare expert evidence on resilience for the Environment Protection Agency so we can get approval for the project. So I was engaged by the client, New Zealand Transport Agency, or Wakakatahi as we call it. So one of the key things is that sea level rise is an uncertain quantum. We all know that there are different predictions in terms of climate change and therefore sea level rise. So rather than design and build a high seawall, which would be costly, more carbon intensive, and obstruct people's enjoyment of the environment, we decided to accommodate future rises of the sea revetment through the design. So we designed it in a way so that we had a berm so that we can come and raise that in the future to accommodate future sea level rises. So you can see how we adapt to progressive hazard events. The next case study is again in Wellington, which is in the southern tip of the North Island. And this is located along a key arterial road, the Chater Street in Wellington, which serves the largest suburb of Karori. So this is a large retaining wall, over 200 meters long and over 7 meters high, constructed 90 to 100 years ago. So there was previous assessment indicated that it is vulnerable to collapse in earthquakes, and there were previous solutions developed by 2 other consultants. So we were engaged by Wellington City Council to design strengthening measures, develop specifications, drawings, and contracts, and subject to rigorous peer review because of the importance of this route. So how did we go about it? We started off developing an integrated ground structure model from investigations we did. We did a Revit model to develop the structure and a leapfrog 3-dimensional ground model to get a model of the ground. And we integrated them to get an integrated model, which we could use to look at the strengthening options of this heritage structure, but also look at the embodied carbon. So the initial original concept was to have a cast in situ wall in front with numerous rock anchors and piles at some of the deep sections only. And that had an embodied carbon of about 400,000 kilograms. So through our refinement, we were able to use a thinner cast in situ concrete slab, working integral with the existing wall, with fewer anchors, but short piles embedded into rocks. So we had good soil structure interaction. So that meant that we were able to get better resilience and 20% lesser carbon, embodied carbon. So the key to this, you can see on the left-hand side, the original historic photograph showing when it was constructed on the left-hand side, and then on the right-hand side, you can see the integrated 3-dimensional model. So the enhanced resilience came from an integrated wall pile anchor system, and we allowed for performance in larger than design earthquakes because we know that these events have significant uncertainty. So we used a resilience-based design so that we built in ductility into the system and to the anchors so it can perform better. And we achieved a significant 20% reduction in embodied carbon and used smart digital engineering to help with the design and help with future asset management. The third case study is of the Ferrymead Bridge in Christchurch. So Christchurch is located in on the east coast of the South Island, which is the biggest city in the South Island. And this bridge provides access to the eastern suburbs of Christchurch across a river estuary in that area. So earlier there was a 3-span bridge which was damaged beyond repair due to the liquefaction and lateral spreading of the riverbanks in the 2010-2011 Canterbury earthquakes. So the client wanted this to be a first showcase project to demonstrate that we can design for resilience and make Christchurch a more resilient city. So that was the challenge set to us when we were engaged to develop and design a new resilient bridge. And develop specifications, drawings, and contract documents, and also manage the construction in an active seismic environment. So the client was the Christchurch City Council. So the key challenges we had is highly liquefiable soil. In fact, it had liquefied, so there's no uncertainty there. Severely damaged bridge and new piers that were under construction for the bridge. We had a very variable volcanic pyroclastic flow basement, so there was challenging foundation conditions even below the liquefiable deposits, and numerous underground services in the approaches which we had to deal with in the reconstruction. And also, as I mentioned, we were working in an active seismic environment with aftershocks, so we needed to make sure that it was able to be insured during construction. so we don't get setbacks during the process. And as I mentioned, there was a high societal expectation for completion of this early with good resilience. So we did that by having an integrated structure geotechnical client team to work together to develop some integrated thinking and solutions. So we use this resilience-based design philosophy to go from this green triangle and reduce that to a blue triangle, where we reduce the amount of loss of functionality, but also enable quicker recovery. So how did we do that? So, the existing bridge got damaged by due to the piers located at the bottom of the river banks. So we decided to have a two-span bridge. So we located the pier in the middle of the river, where it is not prone to so much lateral spreading loads from the riverbank. And then the abutment piles, we used slender piles. You might think we got big loads. Why are we using slender piles? Because if you use bigger piles, we'll get bigger loads when you have lateral spreading. So we used slender piles so that the liquefied ground can flow around it, and we take a lot of the lateral load through the robust middle pier. And then we had short spans, land spans at either end. They act like a fuse. So if you had lateral spreading, you might get some damage to that land span, which you can quickly span over with a steel girder or steel plates, and then repair that quickly to get access. So you can see how we are focusing on not just the functionality, but also ability to recover quickly. And finally, you might wonder, how do we deal with the foundations? So what we used is we used a technique called post-grouting using tube mentioned techniques so that we could enhance the lateral capacity of these piles in these variable deposits. So the outcome was a high degree of resilience through this resilience-focused design approach. The piles were supported during construction to prevent damage during aftershocks. And we had reduced cost due to lesser foundations and also the avoidance of ground improvement, which also meant we didn't have to disrupt all the services. And as a result, we also ended up with less embodied carbon because we had less structure piers, slender abutment piles, and we avoided the energy-intensive ground improvement. And that led to a successful opening of the resilient bridge. And in the process of this $30-odd million project, we were able to save several $1 million. So the final case study is about Transmission Gully. So Transmission Gully is a major expressway north of Wellington here. And it runs through quite rugged terrain with an active fault. And the previous concept was very costly. And we needed to gain the buy-in of a large number of stakeholders because it was a regional project crossing a lot of territorial boundaries. We were engaged to develop a new expressway scheme that is affordable, estimate the cost and prepare a business case for approval, and then also provide evidence to the Board of Inquiry. In my case, I had to present evidence on geotechnical engineering and resilience to natural hazards. The client was the New Zealand Transport Agency or Whakaputahi. So this shows a bird's eye view of the project. The original highway, State Highway 1, went through there. The white line went along the coastline with very steep cliffs and the sea on the other side. So there was no opportunity to expand and had very poor resilience. So the alternative was to build this transmission gully route to relieve congestion. So one of the key things we did was to reflect on the big picture. So I had the opportunity to carry out a resilience study for the whole of the transport network in the Wellington region just before this project started. And you can see on this map the results of this resilience study, and the colors indicate from green to purple the degree of disruption from a major earthquake. And we'll have similar type of issues in a major storm event. And you can see purple and red affects a lot of the accesses in and out of this capital city of Wellington. So when I looked at starting this project, Transmission Gully had the opportunity to provide significant improvement of resilience of access into Wellington. So we as an organization promoted resilience as a key objective and made that one of the key objectives on the project. And this is the first time it became a key objective on a major transport project. And this enabled us to bring integrated focus on resilience with our team. So on the right-hand side is our working drawing. The white alignment was the original alignment, which had a number of viaducts and which was crossing areas with a lot of landslides. And it was crossing the major active Ohio fault at a number of locations, and it crossed them on viaducts. So one of the key things we did was to change the alignment with something like the blue alignment there to minimize the crossing of active faults, cross the active fault on earthworks rather than on viaducts, and avoid hillsides with active landslides, which we'll look at shortly. So one of the key improvements was to cross this active fault on a gravel fill embankment instead of viaducts. Why? Because if a viaduct or bridge crosses a fault, that kind of displacement can't be tolerated, and therefore the bridge would be infunctional, and it will take a very long time to design and replace the bridge. Whereas if you had an embankment, we could quickly use some earth-moving machinery to ramp across the fault rupture and restore quick access, and then repair that quickly as well. So we went with a more nature-based solution. And then we replaced half bridges, which were originally planned, into reinforced soil embankments. Why? Incidentally, I had the opportunity to go to China to look at the impacts of the Wenchuan earthquake. And you can see from this diagram, the number of bridges were taken out by landslides from adjacent hillsides. And we had a rugged terrain here. However well we can design bridges, they are no match to the forces of nature, like a big landslide. So we again changed the concept from half bridges and bridges to embankments and reinforced soil embankments. Yes, they will get damaged and engulfed as well, but we can quickly restore access. Again, you can see the concept of looking at functionality and recovery. We also looked at the cut slopes, and we adapted generally flatter cut slopes. We had cut slopes about 45 degrees rather than more steeper 60 degrees. Why? Because it will be more nature-based, so we have less need for shotcrete and anchors, which are costly but also carbon intensive. So this enabled us to accept small wedge failures but avoid large failures. And therefore, you can see from a resilience perspective, we made it into a little blue triangle. So we'll have small rock falls and wedge failures, but not large failures, which affect functionality. So what was the outcome? We were able to bring future focus to this project, achieve a high degree of resilience, use more nature-based solutions, ended up with a lower carbon footprint. And incidentally, we also achieved a $300 million saving on this $1 billion project. On that basis, the project got wide stakeholder support, and the project was approved by the Board of Inquiry based on the expert evidence we were able to present, and the project was able to proceed. So the key drivers from here is the resilience objective, the early focus on resilience, and the integrated design team we had. And the focus on resilience-based design was critical to get innovative thinking and accommodate nature-based solutions. On the right-hand side, you can see the pre-existing highway I showed, the white line, last year was closed by landslides for a number of weeks, whereas on the left-hand side, you can see the Transmission Gully Expressway was open and was able to provide access. And you can see even in this modest storm event, how resilience was enhanced. So let's look at some key concepts. So in terms of climate change, it requires a twin response. We need to address the impacts which we are facing so that we can improve resilience. We also need to adapt to changes which will happen progressively, like sea level rise. Also, we need to arrest future changes by decarbonizing what we do. The second thing is sustainability. If you had poor resilience, you would have larger detours. If it's a road, you'll have large disposal costs and you'll have large reconstruction. So by enhancing resilience, we can reduce all that. But achieving this sustainability requires early focus on the design concepts, using more nature-based concepts and designing for resilience. So you can see it is a cycle. If we had poor resilience, we'll have increased repair and rebuild. That leads to poor sustainability, more climate change, and more adverse impacts, which further reduce resilience. So we go down in a downward spiral. So that requires us to look at resilience, sustainability, decarbonization, and climate change impacts as an integral whole when we do our design and do our management of our built environment. So to do that, a resilience-based design is important. So we can focus on functionality and recovery, which is important. Sometimes we can recover in one step. Sometimes we might have a stage recovery, initial partial access or partial functionality, and then takes a bit more time to get full functionality. To achieve that, we need an integrated focus on sustainability and an early focus. So that enables us to focus on sites, alignments, and structural forms. And we need to work together as an integrated team. The final thing is resilience does not need to cost more. If we have a mental block that tells us that resilience and sustainability cost more, we can't make progress. We need a paradigm shift in our thinking that we can achieve resilience without necessarily costing more. So we need that shift in our thinking. So to conclude, we are living in an era of uncertainty. We have climate change effects, earthquakes, and the need for decarbonization. We as engineering professionals need a shift in our approach. We need to work together as an integrated team, and we need to focus on designing for resilience and use nature-based solutions wherever possible and bring this early focus on resilience and sustainability. That way, resilience and sustainability does not necessarily need to cost more. Thank you, and now we'll go to some questions, and I'll hand over to Sharon, based in our Canadian office.
Thank you, Brava, for a fantastic presentation. Yes, calling in from Montreal, which is 28 degrees today, which is really not obvious for an autumn afternoon in October. So please continue to log your questions in the question box on the GoToWebinar control panel. The presentation slides are available to download in the handout box, and I will start with the first question. This is a question we received from registration from an individual from New Zealand. What are the 2 or 3 key points currently holding us back from infusing resilience of New Zealand built environment?
Yeah, a few issues. A very good question. I mean, as I mentioned that towards the end, often we have the mental block. We think every time I talk to people about, oh, we need great resilience, people often say, oh, but that's going to cost more. But if we focus on resilience, it does not necessarily need to cost more. And that is one thing which is holding back. The other thing is, as I mentioned, we are basing our designs on standards which were developed and design approaches which were developed a long time ago in more stable environments. I know this has been evolving, but we need a more fundamental shift to think about resilience, because whatever we do and design for in our built environment, we do it for functionality, and quick return to functionality is critical for our communities. So those are a couple of things we need to focus on. And the third thing is that, again, from a carbon footprint point of view and decarbonization, we can have both resilience and decarbonization if we had early focus. Often people think, oh, if we go to focus on achieving better resilience, you're going to have a more carbon-intensive design. But does not necessarily need to be the case. And hopefully, some of those case studies I talked about illustrate that issue.
Thank you. The next question is about the frequency and severity of storms. Is there evidence that there is increased frequency and severity of storms in New Zealand and associated losses?
Yeah, absolutely. I mean, I showed some case studies of how many events we have had. So I had a look at insurance claims over the last 60, 70 years, from the 60s to current day. So the insurance claims have been increasing a lot due to natural hazards over the last 10, 15 years. So that increase indicates to show that we are having an increased impact. I mean, we don't know for sure that it's due to climate change, but that's a good guess that climate change is impacting on having these severe, frequent weather events. Do you have anything else to add to that, Doug?
Sorry, just joining, turning my camera on. I guess in recent times when we've been involved with a lot of responses, that gives us, that direct appreciation of the frequency. But I'd say that the severity is also increasing a lot. That we see not just these localized failures, whether they be storms or anything else, but the wide-ranging impacts. I mean, the Cyclone Gabriel is a perfect example, which affected almost half of the North Island of New Zealand, rather than a localized storm to a specific area. So I think these events are moving across wider areas and causing a lot of damage as they go.
Thank you, Doug.
The next question is regarding the case study number 3. It's a comment and a question. Case study 3 suggested that the ground improvement was avoided. That means that the design philosophy allowed approach embankment to fail, or there was something else included.
Yeah, correct. So we looked at a number of options, including ground improvement. There are two solutions to deal with that. One is to improve the ground, and therefore we have no liquefaction or lateral spreading. And the challenge with that was that there were lots of services, and we needed a lot of ground improvement. Even with a little bit of movement in large earthquakes, you will still have significant loads on the piles at the abutments. So instead, we decided to use a structural approach to make sure that the structure can resist these loads, and we minimize the loads on the abutment piers when you get liquefaction by making them slender, as I mentioned. So by taking a structural approach, we made it more practical, and also were able to accommodate the liquefaction and lateral spreading.
Thank you. Why is early focus so important to enhance resilience?
Yeah, that's absolutely important. Good question. Because if you don't focus early, and I mean, we often sometimes face with these problems, is that people make a decision on the site, an alignment, and how can we then improve resilience or sustainability? We then are stuck with that. And therefore, the only way we could improve resilience is by spending a lot more money, a lot more stabilization, which will become carbon intensive. And still we won't achieve the same level of resilience. Like the transition gully example, case study showed that because we were able to bring focus on resilience at an early stage, we had the ability to change the alignment, and we were able to change the form of construction or the design. So we were able to influence both resilience and sustainability. And it is a similar case with the building project. So if we had a building project, we want to be early there so that we can choose the right site, build on the right part of the site, and make sure that we can build that in a more resilient and sustainable manner. So that early focus is so important to bring in resilience.
Thank you. The next question is for the last case study of the expressway. How was resilience achieved by using embankments instead of bridges?
So I mean, a lot of design from an earthquake design perspective is about ductility and it's about flexibility. So if you had an embankment which is more ductile and flexible, if you had movement of the faults, then it can be accommodated by the embankment. Yes, you'll have a step in the embankment or deformation of the embankment, but that's easy to restore by using earth-moving machinery. Compare that to, or contrast that to a bridge or viaduct. These are rigid structures, and if you have 3, 4, 5 meters of movement, which is what was predicted, then a structure can't accommodate that level of movement. And then restoration of that becomes very costly and very expensive. And that's why using more flexible nature-based solutions has an added advantage when we are focusing on resilience and sustainability.
If I could just add to that, Bravo, we saw this quite exhibited in the Kaikoura earthquake, where fault rupture, there were a lot of fault ruptures, and bridges that were close to the faults or across the faults were badly damaged and unable to be used, whereas where the road or the infrastructure was on embankments, it was much faster to clear, sometimes within hours, if there was a earth-moving equipment available. So, you know, this is not just a sort of a desk-based concept, it's been proven as well in practice.
You're doing that research on the Kaikoura landslides, aren't you, Doug? And you saw some roads which were cracked, but you were still able to get access quickly. Oh, that's
yes,
right.
Yes, that's right. Yeah, yes, yeah. And others where there were structures that weren't able to tolerate the ground shaking, it caused much more damage, and there was no way past. So the functionality was essentially down to zero. And it becomes more time consuming to restore access, or in some cases having to create new accesses, so temporary bridges or fords across rivers where the existing bridge was unable to be used.
Thank you.
Thank you.
I will take the last question, resilience versus decarb. In dealing with the climate change, is it more important, in your opinion, to enhance resilience or decarbonization?
Yeah, that's a good question, and that's what often people ask about. And I think we can achieve both because two things. I mean, resilience is important because we are already facing the effects of climate change, and every year we are having big storm events which are causing a lot of damage in New Zealand, and you can see that globally as well. Every month you hear about severe weather events somewhere around the globe. So that's very important. Now, decarbonization is also important because we need to arrest this climate change so it doesn't get worse. New Zealand contributes about 0.1% to the global carbon emissions. And out of that, 50% is from agriculture. But we need to do our part in the construction sector to reduce the carbon emissions. But so what I would say is that they're both important, but we can improve resilience without significant carbon emissions if we focus on it from an early stage. And the key message I want to leave people with is that resilience and sustainability does not need to cost more.
Yes. Thank you very much, Barbara. Fantastic presentation. We're at the end of our webinar session. Any additional questions will be answered directly by the presenters today. So thank you, Barbara and Doug, for a fantastic presentation. This is session 1 out of 3 from the Resilience to Geohazards webinar series. So we hope to see you in our upcoming sessions. And that's it. We will wrap up the session now. Have a wonderful day, everyone.
Thanks very much.
Thank you. Thanks, everyone.
Thank you.